All right, today we are cracking open the mathematical vault that basically runs our digital lives. We're talking about hashing. It's the secret math that creates a unique digital fingerprint for pretty much any piece of data. And it's what keeps everything from your passwords to your bank accounts secure. So let's dive right in.
It sounds like a total paradox, doesn't it? I mean, think about it. Every single time you log in somewhere, a server has to confirm your password is correct. But, and this is the important part, for your own security, that server can't actually store your password. So how on earth does that work? Well, the answer is just a beautiful, beautiful piece of irreversible math.
You know, the best way to think about the core concept of hashing is to imagine a blender, a one-way blender. It's super easy to throw some fruit, some yogurt, some ice in there and turn it all into a smoothie, right? But could you ever perfectly reverse that process? Could you take the smoothie and get your perfect whole strawberry back? Of course not. It's a one-way street. And that, in a nutshell, is how a hash function works.
And here's the more, formal definition for it. It's a process that's simple to do, but is just practically impossible to undo. This whole idea, this asymmetry, is really the bedrock of modern cryptography. You don't have to hide the smoothie, right? The security comes from the simple fact that nobody can figure out what your original recipe was just by looking at it.
So here's what happens. When you create an account, the website doesn't store password 123. No way. It runs your password through this mathematical blender and stores the result, this long, jumbled up string of characters called a hash. Then, when you go to log in again, it just does the exact same thing with the password you just typed in and checks if the new hash matches the one it has stored. Simple. Your actual password is never exposed.
So, what kind of math actually makes this irreversibility possible? Well, on the left, you've got your standard high school algebra. If you know y, you can always work backwards to find x. It's a two-way street. But on the right, we have something called modular arithmetic. You can think of it as clock math. If I tell you the hour hand is pointing at 2, can you tell me for sure how many times it's gone around the clock? Nope. The original number of hours could have been 2 or 14 or 26. There's just no way to know for sure.
And that's the absolute key right there. The modulo operation is a one-way street, specifically because it throws away information on purpose. It only gives you the remainder, not the whole story. By destroying that data, it makes the path back to the beginning completely impossible to trace. This is the secret ingredient in our mathematical blender.
Okay, so if modular arithmetic is the secret ingredient that makes it impossible to reverse, what are the blender's blades? How does the hash function actually scramble the data so completely? Well, it happens at the most fundamental level of computing you can imagine, the bits themselves. The function uses a whole series of incredibly high-speed operations called bitwise operations. So think of these as the ridiculously sharp, fast-spinning blades inside our blender. Operations with names like XOR, AND, and rotate take the binary code of your password, the ones and zeros, and they just mix, shuffle, and transform it thousands and thousands of times.
So this here gives you a really simplified look at how it works. The input bits get fed into this complex chain of operations, and the output of one step immediately becomes the input for the next one, which creates this incredible cascade of changes that totally obscures the original data. The end result is a thoroughly scrambled, unrecognizable mess of bits.
Now, this intense scrambling leads to a really critical property of any secure hash function. It's something called the Avalanche Effect. And honestly, it's what makes the output so unpredictable and so secure.
Okay, just watch this. It's pretty cool. We're going to take a simple input string, the word explainer, all in lowercase. Now, when we run this word through a standard hashing algorithm, something like SHA-256, we get this long, complex string of characters. It looks completely random, right? Nothing like the original word.
Now we're going to make the tiniest, most insignificant change you can imagine. We're just going to capitalize that first E. That's it. Everything else is exactly the same.
And wow, look at that. It is a completely, totally, utterly different hash. Not a single character is the same. This is the avalanche effect in action. A tiny, tiny change in the input creates a massive, unpredictable change in the output, just like a single snowflake can start an entire avalanche.
So this probably brings up an interesting question in your mind. If we're turning basically an infinite number of possible inputs into an output that has a fixed length, is it possible for two different inputs, like, say, two different passwords, to accidentally create the exact same hash?
That event actually has a name. It's called a collision. And for any hash function to be considered secure, collisions have to be so mind-bogglingly unlikely that they're just, well, they're practically impossible.
The probability here is kind of related to a fun little math puzzle called the birthday paradox. It turns out you only need 23 people in a room to have a 50-50 chance that 2 of them share a birthday. But what are the odds when the number of possible birthdays isn't 365, but something much, much larger?
I mean, the scale we're talking about with an algorithm like SHA-256 is just staggering. The number of possible unique hash outputs is 2 to the power of 256. That's a number with 78 digits. It's a number that is literally larger than the estimated number of atoms in the entire known universe.
So yeah, while a collision is theoretically possible, the chance of it happening by accident is so astronomically small, I mean, you have a better chance of winning the lottery every single day for the rest of your life. For all practical purposes, it's impossible.
And that, right there, is why this all matters. This one-way, avalanche-prone, collision-resistant math isn't just some cool academic trick. It is the silent guardian of our entire digital world. It's what verifies your passwords, what ensures the files you download haven't been messed with, and it provides the fundamental security for huge technologies like blockchain. It really is the bedrock of all digital trust.
Which kind of leaves us with one final thought. We've seen how this incredible principle of an irreversible process secures our digital lives. But just think about it for a second. What else in our world, whether it's digital or physical, is protected not by a lock and a key, but by a process that's really easy to do, yet completely impossible to undo?